Hello, Mr. Betts here. I want to take a look at a power series here and an example of where we want to find the radius of convergence for that power series. So if you remember, we want to use the ratio test to find the radius of convergence. So the first thing I'm going to do is I'm going to set up the ratio that we use, the limit of ratio that we use for the ratio test. So that's going to be r equals the limit as n approaches infinity. And remember, this is going to be the absolute value of the n plus first term over the nth term. And so the n plus first term I'm going to do first here. So it's going to be negative 1 to the n plus 2 times x plus 1 to the n plus 2 over n plus 1 times 3 to the n plus 1. So that's the n plus first term, and I got that just by replacing every n in the expression with an n plus 1. And then instead of dividing by the nth term, I'm going to multiply by the reciprocal of the nth term. So anytime we have a fraction, it's easier, instead of dividing by a fraction, to multiply by the reciprocal. So this is just n times 3 to the n over negative 1 to the n plus 1 times x plus 1 to the nth power. Okay, so again, that is just the reciprocal of that. So to evaluate this limit now, I'm going to cancel whatever I can. First thing I want to do is point out that since we have an absolute value, this negative 1 to the n plus 2 and the negative 1 to the n plus 1, those are just going to go away. The absolute value of negative 1 is 1. So regardless of whether that's giving us a 1 or a negative 1, absolute value just goes away. Let's say the 3 to the n's. So looking at our 3 to the n's here, we have one more 3 in the denominator than in the numerator. So all of the 3's in the numerator are going to cancel with all but 1 in the denominator. Looking at the x plus 1's, we're going to have, sorry, that should have been n plus 1 there. So we have one more x plus 1 in the numerator than in the denominator. So all but 1 are going to cancel there. We cannot cancel the n's. Okay, those don't go away. So I'm going to clean this up here, and I'm going to do a couple of things. So what I'm writing right now is going to be a mental step. So I'm cleaning up, getting rid of the stuff that we're done with. And we have x plus 1 on top times n on top over n plus 1 times 3. Now, in this limit, the limit is as n approaches infinity, and the value of x does not depend on n, and the value of the 3 does not depend on n, so those we can actually take outside of the limit. So essentially, I'm thinking about this as kind of factoring that out. Now, obviously, the n and the n plus 1, those depend on the value of n. So as n gets really big, x plus 1 stays the same, and the 3 stays the same. Now, it's really important here to understand that x plus 1, depending on the value of x, could be negative, but we have the absolute values here. So I'm going to put the absolute values around the x plus 1. That's the only part of this expression that can be negative, so I don't need the absolute values on anything else. Then we have the limit as n approaches infinity, and then what's left over is going to be n over n plus 1. And again, I don't need the absolute values because n is becoming a big positive number. So n is positive, n plus 1 is positive. So the only place where I need the absolute value still is on the x plus 1. Now, if we evaluate that limit, this limit right here, we have n to the first on top, n to the first on the bottom, no coefficients. So that's just going to be 1. So this is going to be the absolute value of x plus 1 over 3. So that's the value of the limit of the ratio of the n plus first term over the nth term as n approaches infinity. And remember, the ratio test says that the series is going to converge if this is less than 1. Okay, so we found r, we found that limit, and then we set our result less than 1. And for the radius of convergence, all I need to do is get it in a form that looks like this. X minus something is less than r. I'm going to put r there. And once I have that, then r is going to give me that radius of convergence. So taking this expression right here and multiplying both sides by 3, we get absolute value of x plus 1 is less than 3. So the radius of convergence is 3. Remember the 3 dots there, that means therefore. So this inequality here tells us that the radius of convergence is 3. Now, I'm going to just change the question here a little bit. Instead of the radius of convergence, let's look for the interval of convergence. Okay, so the only difference is we're looking for the interval of convergence instead of the radius. So I'm going to rewrite this expression right here. So absolute value of x plus 1 is less than 3. And to find the interval of convergence, we want to solve this inequality. Since it's a less than inequality, this is going to be a compound inequality. So we get negative 3 is less than x plus 1 is less than 3. Subtract 1 from each part, and we get negative 4 is less than x is less than 2. So the ratio test tells us that this series is going to converge for all x values between negative 4 and 2. It's also going to diverge for all x values less than negative 4 and greater than 2. But what we don't know is what happens at x equals 4, negative 4, and at x equals negative 2. So to find the interval of convergence, now we have to check what happens at the endpoints. So I'm going to just check those individually. So I'm going to say x equals negative 4. And I'm going to rewrite this power series here, replacing the x with a negative 4. So we have the sum from n equals 1 to infinity of negative 1 to the n plus 1. When we plug negative 4 in for x here, we're going to get negative 3 to the nth power over n times 3 to the n. Now we have a couple of choices here. You can cancel stuff out if you want. So the negative 1 to the n plus 1 and the negative 3 to the n, you can write that as a single expression. That's going to be, what is that, negative 3 to the nth power, I think. What I would actually recommend doing instead of doing that is just write out the first few terms. Okay, so when n equals 1, we're going to have negative 1 squared, so that's 1. Then we have negative 3 to the first power, which is negative 3, over 1 times 3. And so that's just going to be negative 1. Okay, so we plug in n equals 1, we get negative 1. When we plug in n equals 2, we're going to have negative 1 to the third power, so that's a negative 1. We have negative 3 squared, which is 9, times 2 times 9, and we're going to get negative 1/2. And if we continue doing this, every term ends up being negative, and the 3's are canceling each other out, the 3 to the n's. So we had 9 divided by 9, then we'll have 27 divided by 27, and so on. So the only thing that's not really canceling is that n, and we get the harmonic series, but all negative terms. So this diverges. And we want to explain why. We don't want to just say it diverges, but we want to say why that diverges. And we know that diverges because it's the harmonic series. So I'm just going to write that in parentheses. It doesn't matter that it's the negative harmonic series because we can just factor a negative 1 out, and it's 1 plus 1/2 plus 1/3. And the harmonic series itself diverges. So if we take the opposite of it, it's still going to diverge. So at x equals negative 4, this power series is going to diverge. So we don't want to include negative 4 in our inequality. Then we want to check the other endpoint at x equals 2. So we're going to rewrite the power series again, but this time we're plugging 2 in for x. So on top we're going to have 3 to the n, and on the bottom we have n, this should be an n plus 1 here, n times 3 to the n. Now this one's a little bit easier to work with because it's easy to see that the 3 to the n's cancel. And what we end up with then when n is 1 is 1 over 1, which is 1, minus 1/2 plus 1/3 minus 1/4, and so on. And this is the alternating harmonic series. So this converges, Specifically, it converges conditionally. With the interval of convergence, we don't really care that it's conditional versus absolute convergence. And it converges, we can just say we know that it converges because it's the alternating harmonic series. Okay, so that's a known series. That's one that we can just say it converges if it's an alternating harmonic series, or diverges if it's the harmonic series. We could also say that this converges by the alternating series test, because the terms are decreasing in absolute value to zero, and the terms are alternating. So we can say it converges by the alternating series test also. So since it converges when x equals 2, then we do want to include 2 in our inequality. So the last thing we're going to do here is write out a summary, and I'm going to just give myself a little bit of room here to do that. So now we can say, therefore, the interval of convergence is, and you can write it either way. You can write it as an inequality, or you can write it in interval notation. So I'm going to write it as an inequality. So -4 is less than x is less than or equal to 2. So remember, we're not including the -4 because it diverged at -4. We are including the 2 because it converges at 2. So the interval of convergence is -4 is less than x is less than or equal to 2. You could also write it in interval notation like this, and that would also be acceptable. Just make sure that it's clear that we do not include the -4 and we do include the 2.